Yeah, I'm still riding dirty, but I'm cleaned in a bitch. I got the 84s, I got the new Vogues. We chasing old money.
Hi guys, my name is Nako Nakatsuka. I'm a fourth year chemistry PhD student at UCLA, and today I'll be helping you guys out by going over some general chemistry concepts. And good luck with the course. So now we're going to talk about molecular shape and structure, which is a very important topic for you guys to understand. And so the shape and conformation of molecules often determine its biological activity. And so when we talked about Lewis structures, this was a 2D representation of a molecular shape, and it indicated the approximate location of bonding electrons and lone pair electrons. But in addition to this, we need to know the regions of high electron density because those repel one another. And so from here we move into VSEPR, a model which stands for valence, shell, electron, pair, repulsion model. And basically what VSEPR does for us is it gives us the location of bonding electrons and lone pairs with respect to the central atom. And so bonding electrons and lone pair electrons repel one another. And the strength of repulsion goes like this. Let me draw it right here. Strength of repulsion. Where we go from the largest strength of repulsion, which is lone pair, repulsion, which is greater than lone pair and bonding pair repulsion, which is greater than bonding and bonding pair repulsion. And so from here we get molecular shapes. Consisting of the lone pairs as well as the bonding pairs. And then we name the shape of the molecule using the position of the bound atoms. And in this case, we only look at the bonding electron pairs only. And so the VSEPR model explains experimentally observed shapes of molecules. And so we're going to look at different numbers of electron pairs, like so, and I'll give you examples of each different one. But I wanted to also show you this very simplified diagram, where this is drawn showing balloons. So in this case, there is one central atom right here, and there's two balloons bound to it. And in this case, basically, since we have these electron-electron repulsions, these balloons want to be as far apart from each other as possible. Again, if you have three balloons, it's also going to be like this, where you want to be as far apart from each other as possible. Finally, for 4, it would look like this, for 5 and 6. Basically, if you wanted to bind these balloons together, they would take on these forms, which is exactly what these molecules do. And in order to get these different molecules, we need to learn how to draw different configurations and draw these different geometric models. And so now let me walk you through each of the different molecules. So now let me talk about the molecular shape we get when we have two electron pairs. And so an example of this, which is the typical one you'll see very often, is CO2. Knowing how to draw the Lewis structure of CO2, so again, we're incorporating what we learned from the topics before and now moving on to the advanced way of drawing them. So CO2 looks like so, where it has two atoms attached to the central carbon. So in this case, the reason why it's linear with 180 degree separation between the two atoms at the end is because Since it only has 2 atoms attached to the central atom, these want to be as far apart from each other as possible so that there's less electron-electron repulsion. So this is taking on the form like this one, where when you have 2 balloons, let's look at these balloons with the oxygens and the carbon in the center, then they want to be as far apart from each other as possible. So now let's look at trigonal planar. A good example of this is BF3, or boron trifluoride. So in this case, if we drew the Lewis structure, it would be something like this, where the fluorines all have these lone pairs, and then boron makes these 3 bonds. But if this was the Lewis structure, it's not the correct geometry. And the reason for that is these 3 atoms want to be as far apart from each other as possible. So it's going to take on this 3 balloon form. So let's pretend that there's boron in the middle, fluorine, fluorine, fluorine. So this is actually going to end up looking like so. And this is called a trigonal planar geometry, and each of these angles are 120 degrees. 120 degrees times 3 makes 360, right? So basically you're splitting up this circle between 3 atoms to get maximal distance between the 3 atoms. So for this one, tetrahedral, let's look at methane, Ch4. So now you have carbon in the center with 4 hydrogens. So this would be the Lewis structure, but we want to draw them in a way that these hydrogen atoms are as far apart from each other as possible. So the 3-dimensional model is going to look like this, where this wedge right here is showing a bond that's coming out of the page. And then we can also draw a dotted line, meaning that there's a bond going behind the page. And then there's another bond like so. So basically in this case, we're making a tetrahedral structure where you have kind of like a pyramid. If you look at this diagram, it's actually a lot easier to see, where you have carbon in the center and then a hydrogen, a hydrogen, a hydrogen, and a hydrogen that is as far apart from each other as possible in this tetrahedral shape. And so this is tetrahedral. And the angle between these atoms are 109.5 degrees. And so now we've done 2, 3, and 4 electron pairs. So now let's move on to 5 and 6. So now let's look at an example of the trigonal bipyramidal, where you have 5 electron pairs. So a good example of this is PCl5. So when you draw the Lewis structure of it, you have PCl, just randomly distribute 5 chlorines around this phosphorus. And all of these guys have lone pairs, which I'm roughly drawing right now. But in order for these chlorines to be as far apart from each other as possible, they're actually going to adopt this trigonal bipyramidal structure, where the central atom has 5 bonding pairs, but the least amount of repulsion is going to be 3 atoms in one plane, with 1 atom above and another one below. And so it's going to look like this. PCl, Cl, and then 3 in one plane, like so. So as I showed when I did the methane molecule, when you draw this dashed line, it means it's going into the plane of the board. And when you have this thicker line, it's coming out of the board. So this is my way of trying to draw this in a 3-dimensional way. And you end up with these 2 pyramids on top of one another, which is why it's called trigonal bipyramidal. And so the distance between these 2 chlorines on the same plane is going to be 120 degrees. Because this is like you're looking at the trigonal planar molecule from above, right? With P, Cl, Cl, Cl in this plane. But on the other hand, for the chlorine here and the chlorine in the other plane, it's going to be a 90 degrees angle, like it's shown right here. And by looking at the 5 balloon diagram, you can see that these are the chlorines in one plane of the board in this triangle, and then you have a chlorine at the top and a chlorine at the bottom. So now the final one that we're going to go over is octahedral, and an example of this is sulfur hexafluoride, so SF6. So in this case we have F, F, all the way around. This would be the typical Lewis structure, and since it's going to take me a lot of time to draw the lone pairs, just assume that all of these fluorines have these lone pairs around them. But since, again, the fluorine atoms want to be as far apart from each other as possible, for the least amount of repulsion, we're going to have 4 atoms in one plane now, instead of 3 before, and 1 atom above and below. And so let's try to draw that. 1 atom above, 1 atom below, and then 4 in the same plane. So we're going to have a fluorine coming out over here, a fluorine coming out over here, 1 going behind, and another going behind. And so now we have a square base for 2 pyramids again, and that's why it's called octahedral. And as you can see right here, this is the 3-dimensional diagram I was trying to show with the dotted line and the wedged lines. And so all of these fluorines are surrounding the sulfur molecule in a way that's the furthest apart from one another. And so the bond angles in this case is 90 degrees for all of them, which is easier to remember. And so as you can see, we went over 2, 3, 4, 5, and 6 electron pairs, and based upon these different structures, we can create these geometric molecules that are more accurate in terms of the distribution of the atoms around the central atom. But we also have some exceptions in the case where we have lone pairs present, which I'll go over in a second.
Back in the beginning, I was coming for it all. Had to see the bigger picture, ain't no point in thinking small. Started off in the Buick with a dollar in the dream.